Recording in progress.
All right. How long do you have today? Like, how much time do we have?
I'm pretty much free today, so
Okay.
as long as you can do, yeah.
Okay. I've got like maybe 2.5 hours. So I figure that's
Sure.
enough time to get through some CAD, some FEA,
Sure.
and some drawings.
Cool.
All right. I'm going to share and we'll get started. I wanted to start with the suspension geometry because that's like a good place to start. And it's also what you guys will kind of have already.
Yeah.
So I'll explain some of that, and then I'm going to explain what aspects of that are used in parts, like what portion of the geometry is used in the arms or in the knuckle or in like the goofy. And then we'll talk about other components and then like a couple design tips, hopefully, and jump into FEA and drawings.
Sure.
All right. Oh, first thing is you've probably seen me open up like the assembly or the geometry a lot, and they're always easily accessible. You should probably pin them, and you do that by going to open recent, and then you can see these are pinned at the top. If I right click on, no, not right click, sorry. If I just hover my mouse over this, I can pin this to the recent documents list. So you can do that for anything, and I recommend it.
I see.
Oh, C2's here. Hey, C2.
Hello. I'll listen in the background as I study.
Okay, are you sure? We can.
Yeah.
We are recording. Okay.
No,
Um,
I can listen.
Cool. So I just said we're gonna start by looking at the geometry, and then after that, I'll go into like how the geometry affects the design of components, and then we'll go into the rest of the components, and then FEA and drawings. Okay, so let's start by rolling this back to just the geometry. So just front and rear sketches. And then let's show them. Okay, so here we have the front sketch and the rear sketch, which you've seen before, but I'll just go in here. The front sketch is defined by, this is the front view now. Lagging a little bit. A shock right here, which is labeled. And the shock, well, I guess first I should say, this is the center of the car from the front view. This is the ground, this plane down here. And this line right here, which connects back to this line right here, is like the center of the car, basically where the center shaft is. And then the caster plane is the plane that defines the inclination of the footbox and of the wheel assemblies. So like the footbox and the A-arms and the knuckle and the wheel, everything is kind of tilted backward along the caster plane, right? And you guys kind of get to decide what that is, but historically, like it's somewhere between 6 and 9 degrees, 6 and 8, 5 and 10, whatever. And right now it's 7, I'm pretty sure. Okay, so you've seen the drawing before. Carlos already has, or not the drawing, the geometry before. Carlos has a geometry, and his also has a shock right here. This point up here is the top mounting position of the shock. And so it's defined based on like the distance from the center of the car and from the bottom of the car of like the chassis tubes, like where you're mounting. But you can move this point around. So as long as this point is like still touching or near touching a chassis tube, you can change these values to be whatever you want. So like, that's why actually I'll open that right now. In the geometry spreadsheet, which I used last year and which is linked in here, it's one of the parameters, right? The shock length is like the length of the shock at ride height. So right now it's 16.4. The reason I want to measure this, I said I wanted someone to measure the length of the shock at ride height, is because I think this value is like not great. It was just an estimate because I couldn't measure in person, but I think this should actually be more like 16.7. We'll see. And this mount height is this mount height right here. Yeah. So you can see that value changed quite a lot, but it ended up at 18.5, 18.5, and this ended up at 16.4, 16.4, and yeah, okay. So I'll continue to walk through those. The
Wait,
next value,
I have a question. Sorry, Ben.
Yeah.
Can you explain what the mountain height is again? Like from where to where?
yeah, the mount height, I mean, it's pretty arbitrary. You can do it from like any point in the chassis, but I did it
Okay.
from the bottom of the foot box. No, sorry, not the bottom. I did it from like the point on the foot box
Okay.
that is in the same plane as the caster plane
Okay. I see.
up vertically to the shock. So like this shock should be mounted parallel to the caster plane,
Mm-hmm.
and it is like that's a constraint. It's parallel to the caster plane. But you can decide on this distance from like the foot box to where it's actually mounted. And you can measure this as like a straight vertical distance. You can measure it along the caster plane. So like I could, instead of measuring 18.5 here, if I were to just measure like this length of this arm, like of this line, that would
Mhm.
also work. You just need like some reference point and then like a way to dimension where the shock is mounted. So
Okay.
that's not like a critical dimension that you have to copy. Like, okay. Does that answer your question?
Yes.
Okay. So continuing through the spreadsheet, that's the shock length and the shock mount height. The shock lever is the lever arm on the upper A arm. So here's the upper A arm, right? The front view of it. And here's the shock. And you'll notice that two things. One, the shock actually doesn't reach all the way down to the A arm. And that's because there's a tab right here that extends backward towards the shock. So this tab, I gave a length of 1.7 inches. I think it worked pretty well, but you could probably go a little bit shorter if you wanted to, just looking at like how the installation worked this year. So 1.6, I don't know, keep it about this. But the more important dimension is this point right here, which is like the projection of the shock where it like effectively enacts its load. This point has to be a certain distance from this point at like the inner end of the A arm to give you your installation ratio or your motion ratio. So I'll remind you guys of what that is. Your motion ratio is like the ratio of how much the wheel is going to travel divided by how much the spring or the shock is going to travel. And I'm looking for the equation. The equation is given by, this might be it. Not really. It's given by a ratio of lengths and the sine of the spring angle right here. And the ratio of lengths, come on, is your total arm length divided by the mounting length. So this is close. It would be A over B sine theta, where theta is like this angle right here, more or less. I have this in like documentation, but yeah, it's here. It's like B over A sine theta, spring angle. So that's why you need to know, like, first of all, the length of the arm, obviously, but also this like moment arm. So that's what the lever is. And for me here, it is 10.25, 10.25, and it's called shock moment arm, but the text is like horizontal, so it's hard to read, but shock moment arm. So from like this tube to the back of the arm. Okay, so that's like helping with your installation ratio. This is stuff for geometry so far. Hasn't affected parts yet, but I'll get there. So that covers the shock and the upper A arm. The next thing to look at is at the end of the upper A arm, you have like a complex series of lines right here, but this is like the main defining portion of the knuckle. So all this mess out here is the knuckle, and it's like super messy looking, but it has to be to like do the dynamics properly. So you don't really need to worry with this stuff up here. This is the A-arm, like I said. But if you remember, we had wafers that were angled relative to the A-arm. So there's like these tiny little lines that don't go to the same endpoint as the arms, and those are the wafers. But Carlos is worrying with that. So you just have to worry about the end of the wafer, which is this point. Remember, it's not the end of the arm, which would be this point, because that's like effectively not even in the physical car. It's the end of the wafer where the spherical bearing is. So this center, well, this point marks the center of the spherical bearing on top. And same thing on the bottom. We find the arm right here. We find the wafer right here. This point marks the spherical bearing on the bottom. So what connects the two spherical bearings? The knuckle. And I think I told you guys once a while ago, but like I'll just remind you again, the knuckle is not this, like the knuckle does not interface with the spherical bearing exactly. The spherical bearing just sits like underneath it and on top of it, right? So the knuckle is actually a little bit shorter than the length of this line right here, but it's pretty close. And this line along with this line, which is your steering arm, and I think it's named steering arm. Yeah, steering arm. So this line, which is like the kingpin axis, right? The like kingpin axis connects those spherical bearings. This line, which is the steering arm, and this point right in here, this one, those are like exported into another sketch, and that's what defines the base of the knuckle. So I'll explain like in more detail now. Upper A-arm, lower A-arm, the knuckle sits between them. The center of the knuckle right here is, I mean, it's not the actual center in terms of height. You can see it's like defined based on this dimension, and I can move it around if I wanted to. But this like central point of the knuckle where other things are connected is the center of the hole in the middle of the knuckle, which is also the center of the hub, which is also the center of the CV joint. It's just like the center point that goes all the way out to the wheel. So because of that, from this center point, we have like a construction line here that goes out to the center of the wheel, and like sets where everything pivots. So this is like another important geometry that you export from suspension geometry into the knuckle, because that's the center of the big hole. Other things to note in here are the length of this steering arm is not the length of the actual steering arm, because if you think of the knuckle, like much of this length, and I'll go ahead and just pull it up actually, much of like the length of that line called steering arm is just taken up by like the main body of the knuckle, which includes like the center hole and like the wall around it. Okay, I think, wasn't the knuckle accidentally put into FBA stuff? Yeah, it was. Okay, so here's the knuckle. And you can see it starts originally with, that's why. Let's get rid of planes. With this geometry sketch. So we have, this is just pulled straight from sus geometry. You have the wheel, and then like the rest of the geometry is over here, right? On the left. So this is like the outboard side, and you have the wheel, you have the kingpin axis that I was just like pointing to. And then you have this line that goes out to the center of the tire. And here's your steering arm again. And these are like the lines that go up to where the tie rod terminates. So this is the end point of the tie rod, and it's the same point in like the geometry CAD. But if I just go back and forth between this sketch and the knuckle, you can see like a couple things that I was talking about. So how the spherical bearing sits on top and on the bottom. How this point at the end of the tie rod is like in the middle of this mounting hole. Although this distance, actually pretty importantly, needs to be smaller next year because I made it too big. I'm sure you guys like remember that. But then also an interesting thing to note is this center point, which I said was like a central part of the knuckle, is not actually modeled anywhere in the knuckle, and it's not even in the middle of the knuckle. It kind of just floats in space, and it has to because like the really critical mounting points are here and here, but above this mounting point, you kind of need, or above this one of the two, you need a straight portion of material because this has to be straight. So you can't have like the whole thing curved or this won't install. And the other reason that it kind of has to look like this is that based on the stack up in our wheel assembly, which is from like the CV joint to the knuckle to the hub, which is right here, out to the tire, it has to be spaced so that like, let's see if I can illustrate this better. So that the hub sits like this. And then that when we bolt the rim on, it's like at this point. And that's already taken care of where like the point that we bolt the rim on is this line, this space right here. But because of that, and like the current design of the hub, which gives the hub a length of like whatever this is, one point something, or it's actually this minus a little bit. It's like 1.5 inches. You really can't like push this face and this face to the left so that they can like sit on top of this point. They kind of have to be where they are. That was kind of a sloppy job of explaining, but I hope like that makes some sense.
It does.
Okay.
Yeah.
Cool. And another thing to note is that from this point out to like the center point of the tire, I think is what it is. You just want the X component of this. That gives you your spindle length. But that's like a measurement that I think I talk about in the suspension Bible, or Millikan talks about it or something like that. It was before it was incorrectly modeled as the length of this member right here. And I might have even kept it that way because it's just way easier, but technically it's supposed to be to the center of the tire, I think, not to where the rim is. Because if you remember, the rim of our tire, like the face that we bolt to, is not in the center of the tire. It's offset. But spindle length as like a number doesn't matter that much. The only thing that does matter is the effect of spindle length on scrub radius, which is a geometry thing, and I'll go explain that right now. So we have the knuckle in here. It's based on this geometry. The upper, I gotta plug it in. The upper A-arm is based on like the weldment, pretty simply. The lower A-arm is the same, also based on like that lower tube sketch. And that's pretty much all that we can like explain as a sketch when it comes to parts. So I'll jump into some of the like geometry considerations that come from this, and then we'll go into actually like modeling the parts, because I think that's the next thing. Oh, well, I guess the wheel kind of comes from this, but this is a sketch block right here, the wheel, called block 1-7. And you can just like copy paste this into other drawings. So you don't have to design this, like this is done. Okay, so from all of this stuff, going back into the geometry spreadsheet, we have the shock length, the shock mount height, the shock lever, which is the moment arm, the length of the upper arm, and I should say the length of the upper arm is measured along the bisector. So you make like this dashed line here, and then you go from this back line to the outermost point. You don't want to measure like one of the tubes because that's not going to be right. And the same thing with the lower arm, it's the bisector of the lower arm. So in their final states, the upper arm is 16.8 and the lower arm is 17.9, 17.9, 16.8. So that's still accurate. Then the length of the tie rod. I didn't touch on the tie rod. It's hiding in here. It goes from the end of the steering arm, which is this point, right? And really quickly, I'll explain what these are. This is a length that you can choose that like sets the length of the steering arm. This is a height that you can also choose that sets like where in Z the steering arm is located on the knuckle. This what right here is what sets like the position of the hole relative to the center. So like if that were 0, the hole would have been right here. But there's a reason we want to have this like pushed in this direction. And that reason is the steering force is like going from the bottom to the top of my screen when you steer, and you kind of want a bit of angle, like so there's more material in the load path. Otherwise it's like more stress on that corner, on this corner.
Hey Ben, random question.
Yeah.
Do you know the wheel block that you have that are just the rectangles?
Yeah.
Are they modeled after like a tire, or did you just like randomly draw those blocks?
I didn't draw them. I think Kevin drew them, and they're modeled after tires. Yeah. The important stuff to take from them is the diameter of the tire. Like we have to make sure that's right, and you can edit that if you need. And then these two lines, there's one right here and one right here. And those two lines allow the wheel to like have its axis set and then to pivot. And this is the line you use to like enforce that pivot. And you do that by like drawing these other lines that run out to it and have perpendicular mates to it, so that when these turn and they're turned by like the turning of the steering arm, basically, because they're perpendicular to the steering arm. So like the steering arm pivots when the tie rod changes length. That steering arm causes this to pivot because it's a perpendicular mate, which causes this to pivot because it's a perpendicular mate. But yeah, this line right here, which is the pivot line of the wheel, this line, which is the center line of the wheel, and this line, which is the diameter, those are the only important ones, really. Okay, so going back to the steering arm right here, you can choose this, it's the sideways length, choose this, it's the vertical position, choose this, it's the forward back position, and it should be a bit inward like this. This 1 inch value right here, and you'll see one on the other side as well. This is to model the rod end. And you should definitely include some line of like arbitrary length, but maybe it's an inch, maybe you figure out it should be 1.25 inches, 1.5 inches, whatever. You should include some line in the sketch that takes up like the space where the rod end is supposed to go, because it makes it way easier to then make a tube that's the right length for the tie rod out of just this inner portion of like line. Because if you didn't have these rod end pieces on either end, you would have a tie rod that in the CAD is 19.5 inches. And when you try to export that and make a tube, like when you make the weldment based on this line, the tie rod's going to be 19.5 inches. And then you have to like do another feature to cut it down. But if you have this line in here to start out, it's 1 inch on either side for the rod end, it makes it a lot easier. And you can see I did it with the A arms too. And those are 1.5 inches because the rod ends are way bigger. And they all say rod end, rod end, rod end, rod end. Yeah. Okay. So that's the tie rod. So So I think that now is all the components that are like really sketched out in here. As for how this all like moves and is like defined, I kind of want Carlos to be the one taking lead on that. So I think like he's got a good grasp of it. And if you guys like want to know more about that, go to him first. I would say you can come to me if you like can't answer something. But I kind of just want to keep this to designing and not to like to part design and not to sketching the geometry. So really quickly, because I said I would talk about it earlier, I'll go over some of the driven dimensions. So your scrub radius down here, which I mentioned, if you project your kingpin axis down, let's see, where is it? There, downward to the ground, it's going to hit at some point, and I have it coincident to this point. And then if you measure the distance from that point to the center of your tire on the ground, that's your scrub radius. As far as is pretty small. The track width, pretty simply, is from the center of the car to the center of the tire on the ground. The ride height is from the ground to the bottom of the chassis, which is this member or this line right here. Actually, it's to the center of the chassis tube, technically, but whatever. Okay. The track center, or sorry, the track width to the wheel center, which is the value that you care about for dynamics, like MATLAB or calculations, that sort of stuff, is basically the same as track width on the ground, except that it is supposed to be taken at the center of the wheel. So this dimension is actually taken right here in like from this point at the center of the tire to this point across from it. And this is what you'll plug into MATLAB. You can see it's slightly different. It's basically the same thing, but like if we're being particular. But the dimension that is like fitting through the shop door, where our maximum is like 60 inches, is not this one. That would be measuring from like the outer edge of the wheel, not the middle of the wheel. And for that, you add like 5 inches, I think, because we have, no, 4 inches because we have 8-inch width tires, I think. So that gives us like 29 and a half and 29 and a half. And then we actually measured it to be 60 instead of like 59. So it's pretty close. Other things, this is the misalignment angle of the outboard CV joint. And it's really tricky to like describe how this is modeled. But it's basically from this line right here, which is the line that I said like defines the spindle, or at least has like the same orientation as the spindle from like the center of the knuckle through to the center of the tire. It's this line to the half shaft line, which is this right here. And the half shaft line goes from, again, the center of the knuckle to the output point of like the front diff, which is not set by you guys. It's set by PowerTrain. It's a little more complicated than that, but that's basically where it comes from. Up here and down here, this is the misalignment angle of the spherical bearing, and that goes from the line that is perpendicular to the wafer to the line that defines the top face of the knuckle. So that's also pretty complicated, but basically the misalignment angle in the spherical bearing can be physically intuited as like the angle between the wafer and that top plane of the knuckle, because the bolt goes like down and mates to the knuckle on the bottom. Like the nut is what defines the angle of the bolt. So that is the top face of the knuckle, but the outer rim of the bearing is seated in the wafer. So the wafer to the top of the knuckle is like the misalignment angle. And because of that, the most effective way to measure it is to make these two lines that are like perpendicular to, let's see, this one's, it's so small though. It's perpendicular to one of them. Yeah, okay, yeah, this one's perpendicular to the wafer and this one's perpendicular to the knuckle, which is defined by this line or some other lines, like there's a few choices. Yeah, so that's the spherical bearings. All of these dimensions in here that have like heights and lengths that are related back to the chassis, those are mostly set by chassis, but suspension has a decent amount of input. And that's saying like, where is the footbox tube that I can mount the A-arms to? How wide is the footbox? How wide is the rack in the steering assembly? And that's like what mounts to the tie rod. That's like this right here. This is the steering rack, 10 inches. And I think you get like the gist of this in here. You guys will definitely want to loop Carlos in for those integration talks where you're discussing like chassis geometry and steering assembly geometry, because having like different values for where the arms are mounted is like going to affect the dynamics of the car. And there is like usually a better answer for suspension. Typically, this is like a blanket statement and not always accurate. Typically, you want suspension to have long arms, like long A-arms, because it's like better for the arc that the wheel follows, and it also allows you to have a better installation ratio. And typically, you want the front to back spacing of the A-arm, like from this point to this point, to be wide, because that means the A-arm is like wider, and that allows it to take load better than if it's narrow. Because if it's very narrow, like the bottom is almost too narrow this year, it basically just takes a lot of load in bending, which is bad. It's acting like a beam in bending. You would rather it be wider, like the upper A-arm, because then when it takes a front load, a lot of that load can be taken axially as if it were like a two-force member. And the way that you can conceptualize that is think of the extreme cases. So if we have a force that's coming from the left to the right of the screen, right? And in one extreme case, the A-arm is just a line going straight back to the chassis. All of the force in that case is going to cause a moment. This tube is going to be in severe bending and it's probably going to break. The other extreme case is you have force coming from the left to the right of the screen, and these have become so wide that basically they form a horizontal bar with like a slight dip in the middle. So I can't show that with my cursor, but they would follow like the path of my cursor so that it's like nearly horizontal, then there's a point, and then it's nearly horizontal. And if that's the case, this rear arm is going to take all of the front load in compression, which is good. That's what you want, because like tubes are way stronger in compression than in bending. That's like the whole point of a tube. And that's going to be like much stronger. So because of that, intuitively, you want the arms to be wider. And the reason that you want them to be longer is not as intuitive. And like I said that earlier, but trust me. But that's not every case that you want them to be longer. It is every case that you want them to be wider. Okay, do you guys have questions so far?
So what is the reason why we can't have a wider lower A-arm this year?
The reason is that if we look at the chassis, it was just designed with like a narrower portion of tube right there. So I used like as much tube area as I was given. But we just didn't have a lot. Oh, actually, I can just go into the assembly. I think that has the chassis, right? Come on. What the heck? It's open in 19 seconds last time. What's going on? Hello? Bruh. Probably gonna crash. No. Didn't crash. But I just closed it. And there it goes. No. Ah, shit. Damn it. All right, I'm gonna close everything and reopen. More SolidWorks is gonna throw a fit. Okay. So I will show you the chassis in a second, but yeah, I asked for more like beam to mount the A-arms to. And I got it in for the upper arm because like initially I didn't have much beam there either. But for the lower arm, based on like the geometry that they wanted to use for the front bracing member, which is no way. The suspension assembly was not there just now. I wonder if it corrupted the file. Based on the geometry they wanted for the front base bracing member, which is like the front of the chassis, like in front of the driver that goes down to the bottom. There like wasn't enough space unless they made the footbox way longer, but that just would have been kind of unnecessary. Okay. Oh, good. Well, we don't even have a chassis. I think they moved it around. Hmm. I don't know if this is gonna work. Okay, chassis did something weird with their files, so we're just gonna not fix it right now. But yeah, the lower tube I just didn't have more room because like right after this point it started bending up towards like the top of the footbox, and we didn't want to extend it more than we already had. And this point was already butting up against the bottom of the tube from like the front bracing member, which ended like here and then went all the way up to the top of the car. It's this one. If you can visualize that, it's so hard without the actual chassis though. Okay, let's talk about generating the arms from the sketch. How about? So let's go back into, unpinned it, no way. Let's go back into geometry. So where we were and what I had done, I just had rolled this all the way back, which you can do with the blue bar here to like suppress everything afterwards. And we just had the sketches. So when you have the sketches right here, if it were a normal 2-dimensional sketch, you could not do this. But for a 3-dimensional sketch, what you do is you go to Insert, Weldment, Structural Member. So I'm glad this is recorded because that's like something you have to like memorize. You don't go to Structure System. You don't go to Feature, which is where you usually go for Insert. It's Insert, Weldment, Structural Member. And now I can choose from any of these like tube libraries. And you see I have this one called VR3 Weldments, which I added a long time ago. And I don't remember where it's stored, but Nico does. I would ask Nico or Takeo or Rayshawn. VR3 Weldments, we want a round tube. And this is like from them, it's all of the tubes they can make. So they might update it next year and have like different thicknesses or something, but round tube. And then these are like all the choices that we have. So this is where you choose the outer diameter and thickness. So like for the load bearing arms this year, I think they're 1 inch by 0.58 and the non-load bearing are 1 inch by 0.35, but we can double check that right now. So let's say I want 0.58 for this upper arm, which is load bearing. All you do now is go into groups, click on the tube. That's it. Pretty easy. It also auto generates these cutouts for you, and they are called corner treatments. So you can see this one has like one tube cut entirely and the other overlaps it. If I flip it, the other tube is cut entirely. If I want them to join at the end, it cuts them so that they like meet up. You can have a gap here, which we don't want. I mean, if you did something tiny like 5 thou, that would actually be good for welding, maybe, so you don't over constrain it, but we've never done anything in the past. And that's pretty much all you need. You are gonna have to do like a lot of cuts and modifications to these tubes after they're made for the wafers to be included. But for the simpler tubes like the tie rod and if you have like no 4-wheel steering, the tubes back here which don't have spherical bearings and wafers, you can just basically leave them as is and you're done after you do the weldment. So let's just go ahead and pull this down and see what the actual tube thicknesses are. So here you can see the upper arm is in this folder called front upper. And yeah, it's 1 inch OD by 0.65 thickness. So that's actually, I wasn't sure if it was 0.58 or 0.65. 0.65 because it's load bearing. But then the front lower is in this draft 0.49, but I think when we sent them the CAD files, we actually told them 0.35. I think. We can probably check this by like, well, measuring in this gap if we have a spare and we can fit some calipers in there. But it's also up to you guys what you want these thicknesses to be. I would recommend for non-load bearing arms that you make them either thinner, so make them either 0.35 or make them a 3/4 inch diameter. Because we want to save weight on the arms, they're pretty heavy. And when they're non-load bearing, they don't need to be that strong. And what I mean by load bearing is it attached to the shock, yes or no? Because if it is attached to the shock, you hit a bump, the wheel goes up, the shock compresses, and eventually the shock compresses all the way. And now this arm, but only this arm, is stuck from pivoting higher and has a force on it from like the other end, like going up from the wheel. So only this arm is really seeing like a big bending moment right there. When there's a front impact, the front of the tire gets hit. It's going to push this spherical bearing back. It's going to push this spherical bearing back. And that is the load case that should be like what you use for the non-load bearing arm, because it, in that case, is going to see some stress and some bending. But if the non-load bearing arm, so if the bottom A arm is wide, you can make it really thin, because that means like the geometry is set up well so that it can like take that front impact, right? We talked about that. And because the geometry is set up better, the thickness can be lower. This is 049 in the CAD because the lower A arm is not very wide in my designs, but I would like it to have been wider, and then it would have been 035 in the CAD. But I'm not sure if we told them 035 or 049. Whatever the
just
case.
play around with FEA analysis, right, to adjust the
Yeah.
geometries. Okay.
Yeah. The only tough thing with FEA on the arms is SolidWorks does not like this interface right here to the wafer.
Okay.
So it takes like a lot of remeshing and some simplification to like make the FEA run the way you want.
Wait, you showed us the structural member part, but that was like fully extended without considering the wafer, right? Or like,
Yeah.
it didn't have the wafer holes in it. So once we get the wafer dimensions and like once we like figure that out, we have to cut the holes back in the A arms again, right?
Yeah, here. So front upper, I created a plane that's like along, and then I created another sketch just for these arms based on the 3D sketch. Then I created this tube, the center tube, and then there's a feature called trim extend, which is also under weldments. Once you have existing tubes, this is the best way to like trim a tube around another tube or extend a tube up to another tube. To like work with your weldments. And now we have another trim extend right here. And this one, I think, is how one of these is how I chopped off the end of the tube. So this is like all you can do with the weldment features. And then you have to go into your like normal sketch features. And this is front upper wafer right here. So right before this point, it looks like just tubes. But then I create this revolve feature right here. This is another sketch block. You'll want to copy this exactly, like to the fraction of an inch, exactly. Because this sketch block, it's kind of weird to think of it like in this shape, but this defines all of the material that you need around the spherical bearing, and then you revolve it, and it creates the cup with like the retaining ring cut out and the lip on top and like just enough, oh my God, just enough material around the edge to like keep the bearing seated well. So you create this circle, and then you create the like legs. And at this point, they're still going like straight into the tube. But then this last cut right here is a cut that like removes the rest of the welded tube that's like overhanging. Because like before this cut, it looks like that, right? The tube is still extending all the way into the wafer. So you make this last cut right here to remove all of that material. And then you make one more cut that I believe is a trim extend to make like this tube cut around this leg and this leg and this leg. Because right now this tube is still like a full tube. So you can go this far with just weldments. Then you sketch in the wafer and you go this far, and then you have to use one more trim extend to like make it fit perfectly. And you have to do that for all the arms. And now it's cut around. So now like there's a cut here. Yeah, do that for all the arms that have a wafer. Yeah, so that's, I don't want to make it sound like it's simple, like, oh, that's all there is to the A arms, because they're really tricky. But like, refer to this CAD because I did a couple things wrong. No, most notably, I pointed out in the sketch how like you should make room for the tie rods. Or sorry, not for the tie. You should make room for the rod ends at the end of your arm. I didn't do that at first, and I had to like cover it up with a bunch of features, and that was a pain in the ass. It's way easier if you have like a line that's the correct length first. So you should do that better. But the rest of the steps I took are like, I think, pretty clear, and I tried to organize them so it's like in these little folders where possible. But some features like wouldn't let me drag it in. I don't know. But yeah, you make your sketch, you make your weldment, you trim the weldment until the tubes are like close to the right size. You add the wafer, you cut the tube, and you cut the tube for the legs. That's pretty much it for designing those. Would you guys rather me go into like part specific drawings and FEA for every part, or should I do like design the arms, design the knuckle, design whatever, and then FEA the arms, FEA the knuckle, FEA the whatever? Which is better?
Doesn't
Whichever
really matter
makes-
to me. Yeah.
Whichever makes sense more in terms of the
Okay.
entire like design cycle, I guess.
Okay. I think I'll go into. Well, if you want it in terms of design cycle, like chronological order, it would be design everything first. But that kind of comes with FEA. Okay, I'll try this. So I'll try to do the FEA with the design, and then we can do the drawings after. Okay, so the A arms are really tricky to model well in SolidWorks FEA. It's just like not great. Oh, no way. Delete all of them. Well, I had FEA in here. Okay, I guess I'll set up a new study and I can like explain things as I go. So the reason that the arms are tough to FEA in SolidWorks is that it wants to treat them like tubing, which is like a different solver than parts. So like it's not treating the arms as if it were an aluminum part or a steel part. It's treating it as if it's like a simple tube, and there's like way too many assumptions that you make in that method. So this is just aesthetic. Way too many assumptions, and it's horrible. It's like very inaccurate, and it doesn't want to mesh very well. So if you have a tube in your SolidWorks FEA, it gives you like all these points here, which are bad. You should never run an FEA in SolidWorks if you're looking at these points, because that means it's making tube assumptions. So how do you fix that? This is like all of the parts that are being considered here. And usually we don't even go into this folder, but you can see all of these right now are beam members. And that's a picture of a beam. So instead of treating this as a beam member, you want to treat it as a solid. So you would have to go through and right click every single like sub box that looks like a beam and make sure that SolidWorks treats it as a solid. So where is this? Which tube did I just do? I just did this tube. So now we have like one normal solid in here. But you have to do this to every tube, and you should only do it to either the front or the rear at once. Like you should only model and FEA the front or the rear arms. And ideally, you should only model like the front upper A arm, and then you should only model the front lower A arm. And that's a huge pain. It's not hard, it's just tedious, because you have to go through and figure out like which tubes belong to the assembly that you want. And then if you don't want it, you exclude from analysis. But if you do want it, you model it as a solid. So I'm just going through and checking like for every tube that is in the assembly I want. And if I don't want it, I'm excluding it from the analysis. But if I do want it, I'm going to treat it as a solid. Oh, so this one is already treated as a solid. That's nice. You did it for me. I could make it a beam if I wanted to, but you know. So I want to treat that as a solid. This is already being treated as a solid because it's a wafer. Same with this one, but I don't want it. And same with this one because it's a wafer in the back. Okay, so now the only thing that's in the study is the front upper A arm, which is good. And we don't need any joint groups because that's just for beams, and we got rid of them. Okay, this is kind of tricky because we still have, according to SolidWorks, some disjoint members right here. What we can do is a couple things. First, you can go back into your model if you want, and you could do like, is it a merge command? No, it's a unite command. No, it's a combine command. You can combine the bodies so that they are like one cohesive tube. And now we have like one part according to SolidWorks, which is going to be better for FEA. But then when you try to export, it's going to be like harder to do the drawings well. So what I did at one point in time is there. I did some combined features, but I did them in a different configuration called for FEA. So I just like, it's broken now, but I don't want a derived configuration. I want a new configuration. Okay. No. What the hell? What is wrong with you? Okay. So if I call this for FEA, and then I do that combine feature for the front upper A arm, combine all of these. Okay. Now I'm gonna actually have to copy this study, but use this. Okay. And then I'm gonna delete this. You have to like make a new study when you change your configuration. Okay, so this should still have all of these considered as solid bodies, but now they're going to appear as one solid body and the rest should still be suppressed. So yep, we do have that. Now is the next tricky part with doing FEA on the A-arms, the fixtures, because the way this is actually fixtured is with a spherical bearing on this end, and that's like really difficult to model. And with a load on this member here from the shock, which is difficult to model with like a fixture on the shock. So the load cases we have for the A-arms are a front impact and a bottom impact. We'll do the bottom impact right now. And that means that the worst case scenario for that is the shock has bottomed out entirely so that this member can't go up anymore. And we're still experiencing load from the bottom of the wheel. So to model that, we're gonna have, ideally we would have the tab in here and we would just like put a fixture on the member. But instead we're gonna do an advanced fixture using reference geometry down here. And we want it on this face. But another thing that I did back when I did this FEA was make a split on this face. That like marks the point where the tab is. So I'll do that too. I'm going to sketch on this front upper plane. Where am I? Why did I put it upside down? It's not that. Okay. So here's the top view now. We're looking at this beam right here, and this is where the shock is mounted. So I'm just gonna sketch here. I'm gonna put this center point on this line. And I know that the length of this is 1.18 plus 0.1 plus 0.1. It's like 1.4. Okay. And now I'm going to do a split line, project onto the tube. Okay, so there. That was what I was trying to do. Let's see if it transferred over. It might not have. Please. Oh. Did it work? It worked. Great. Okay, so going back into the fixtures, what I was going to do was an advanced fixture onto this face using reference geometry. And we want to have, this is your reference geometry. We want to have no translation along this point. So, no. There. No translation, sorry, along that line. So this is what we're looking for right here. Because we're modeling the shock as bottomed out and this is fixed. So that's good. We have a fixture here. That's what we want to see. And then we also need to model these as like rotating, but that's also hard to do. So we're going to have an advanced fixture. We're going to use reference geometry again. We want to put it, and this is kind of sketchy, but how I've done it before is you reference this face, and then you use this jump. No, I want the point. Okay. Okay. But I don't want translation. Not did I do this before? No. No. I did this in ANSYS, which behaves differently than SolidWorks. All right, just for right now, and this is not a good idea usually, we're going to no. We're gonna just fix this outer face right here and this one as well. What you guys probably would do to improve upon this is like create another little portion of the CAD that extends out to this point so that you can have like a cylindrical mate, or I mean a cylindrical fixture, or a spherical fixture. But I can't right now, and it's not worth the time to do that. So we'll fix it for now. You guys should improve upon it. You could make that change in the configuration we have, right? The 4 FEA configuration. So that it doesn't affect like the main assembly. But for now, we're fine with this, I guess. We have fix here. We have the proper constraint here. And then we're going to put our load as a remote load. So for remote loads, which is basically all that we have for like suspension, because nothing is taking a direct measured load. It's all like an approximately known load at the wheel that affects other components. So if you hit a bump and you have like a bump load from the bottom of the tire, that load is being applied to this face by the spherical bearing. It's being applied to this face by the retaining ring of the spherical bearing. And it's probably getting absorbed a little bit by this face too, because it's not going to be perfectly vertical. Really nowhere else. Like you could maybe say some of the load is being experienced by the bottom of the wafer, but if you do that, it's probably going to tell you your design is way safer than it actually is, like way stronger, because this is a lot of surface area with like strong welded metal behind it. And in reality, we're not actually that fortunate. It's kind of all being eaten up by the wafer on the end in the bearing cup. So that's where the load's being applied. We're going to use the global coordinate system, I guess, but you can also create your own coordinate system, like at the center of the wheel if you want to. And then we're going to put its location. This is the location where the load originates. And we're going to use this coordinate system down here. So from the center of the car, I think it's like roughly 25 inches in Z. And we'll be able to check this as we like enter the load to see if we put it in the right spot. And like a couple inches in Y, and then half the wheelbase. So like, oh, sorry, bottom of the tire. It's like minus 11 inches in Y. I'll have to change this. And we're looking at a pound force in Y. This is irrelevant because we have pound force. If we wanted it to be a moment, we would include this right here. So like if we were using rotational components, we would include this, but right now you don't need any translational unit. That the reason it exists at all in this box is you can apply a load as a translation, like as a displacement, but we always apply it as a force. So the force we're seeing is usually for a bottom impact, 3 Gs by a quarter of the car. We've also said half the car before, or 2 Gs by the whole car. It kind of depends on like what your thinking is like for the year. And I'll write this out in the suspension Bible as well. But hopefully we're going to have some like concrete data to derive these loads from soon. And hopefully we see that all of our loads historically have been a huge overestimate. I think we will. But we're going to do 2 Gs by the full weight of the car as if we were like landing a big jump on one tire. And that is just 2 times the weight of the car, which is like 550. So this is probably way too much, but we're going to give it 1,100 pounds. And now we can check whether this is at the right spot. So we want it to be at the bottom of the tire. We did all right. It's kind of close. We're going to make Z 30. No, we're going to make Z 35. Remember, it's the bottom of the tire where it hits the ground, not relative to like the caster angle. So it's actually this point that we're going for, not this one, because this is castered. Okay. And then it should be like that. Okay, so now this is pretty accurate. We have a ground load going straight up through the tire. Yeah, straight up through the tire into like the correct faces of the wafer. And all of this can be left the same. This is a pretty strong load. Okay, the reason that FEA sucks for the arms, besides the whole like beam thing, is that it never meshes. So I guarantee you guys this is not going to mesh the first time. Let's do curvature based and make it fine. And the reason is there's a lot of tiny little lines in the arms. Oh my God, it worked. Okay, well, usually that doesn't happen because there's a lot of tiny little lines in the arms, like right here, tiny little faces, and SolidWorks hates tiny little faces. This is a really bad mesh because all the load is here and it's like super, super coarse, but I'm shocked it worked. So that's a start. But
So
either
if
way,
it doesn't
we're gonna-
mesh, If it doesn't mesh, like what would you do?
The same thing we're about to do. If it doesn't mesh, what you want to do first is go apply mesh controls. Because usually the reason it doesn't mesh is that there are features that are too small to be like covered by the mesh. So then you go select all these like tiny little features here. Oh no. And you just make them have a really, really small mesh size. So I just have selected the entire wafer in the past and given it a super small mesh size. And you got to make sure you hit like every face, which is kind of tricky because it's hard to keep track. But I think that's all of them. And then another place it fails sometimes is around here. So like I've selected these faces before. And then another place it fails sometimes is like around here. So just you keep selecting things, but it seems to be behaving right now, which is great. It might be because I did the combine feature. I don't remember how quickly it worked when I did that last time. I didn't think it was this quickly. Okay, am I missing any faces? I don't know if I clicked this big bottom face. I don't think I did. No, I did. Okay, so we're gonna make these just like absurdly fine. And you can even go finer than this allows you. If you just like type in a value, like we probably want less than 70 thou, we probably want like 20 thou. So we're gonna do that. And then we're gonna try to remesh. And this should look, if it works, way, way, way finer out on the wafer. But it's also gonna take longer, naturally. It has to think more. $20,000 might be too fine for the two that I clicked. So potentially we'll have to like change that. Come on, SolidWorks. Come on, SolidWorks. You can do it. Some other stuff. We'll give it another minute. And if it doesn't work, I'll change the mesh control. Last chance. Okay, let's change the mesh control. We're just gonna get rid of most of the big faces. Oh no. Where it got stuck right there was meshing split line 6, which is the big split line on the crossing tube. That's the only split line in this part. So we're gonna get rid of this for sure. We will just refine that if the FEA is like high stress right there and we want a better look. So just having all this clicked now. Let's try again. It's just the bearing cup. Wow. That looks pretty good. So we have a super fine mesh now here in the bearing cup. Great. It automatically did a finer mesh around tight curve. That's why I chose a curvature based mesh. And it mapped this pretty well. Okay. Reasonable. Let's try this. I'm hopeful this could work. I didn't expect to actually run FEA on the arms today. It's usually such a pain to set up. But yeah, this is simulating like a worst case bottom impact where we've gone off a huge jump and landed on one tire. It might not run perfectly. Oh, there's a chat. Something. All right, so yeah, we do want to refine the mesh here because as expected, it behaved pretty badly at like this edge interface. And it says we're gonna fail. So let's go ahead and ISO clip. We want to look for any part that is going to fail above the yield stress, or any part that's going to see stress above the yield stress. So that is actually where we are right now, auto generated. And it thinks it'll fail here, along with like around this tube and here, and also in the bearing cup. So this is bad because it tells us the arms are going to fail, but the real reason it's bad is it doesn't match history. Like this has never happened before. So most likely, and this is why I ended up like dropping some of our loads. Most likely the loads we're using are bad. Another reason that it could be telling us we have really high stress is that this should not be fixed. Like this should be allowed to pivot a lot. And you can see that what's happening is like the whole arm is deforming up. Usually the deformation would like be allowed to release some of its stress effectively, some of its strain back to the rotational like mechanism here, but it can't right now.
But if
so those, yeah.
If the shock is like fully compressed, right, we should like regard the ends as fixed, right?
We regard this as fixed because the shock is compressed.
Okay.
Because that's where the shock is mounted. But this can technically still pivot if needed. It shouldn't see any stress. So like maybe this doesn't matter at all. But
okay.
The bigger issue is that this doesn't match what's happened before. So let's change the remote load. And this is the load case that I was using once this happened. And I was like, oh my God, that like doesn't make any sense at all. I was using 3G quarter car or 2G half car, which come out to be like pretty similar. 2G half car is just like the weight of the car, 550. And 3G quarter car is 3 times like 150 or 450. So 2G half car. This is half the load we just used. And then we're also going to apply another mesh control to the line. And the reason this works is that if you apply a really tight mesh control to a line, it actually causes all of the elements around that line to still be smaller than they were before, so that it can like have a gradient that meshes back to the rest of the part. Right. This is kind of following a couple of the steps that I ended up taking last year, where we dropped the load and then like figured out where to refine the mesh. So this looks better. This looks good. The load should be better. This is very close to an actual study that I ran last year, but it was in ANSYS, which is better. We're going to cut A-arms right after this and jump to knuckles. What the heck? Okay, so it's just failing on the edge right here, which is probably not real. But like when it's affecting this many elements, it's probably real at that lower stress. But like you can see here, that's fake. In ANSYS, this did not show up because it has a better solver. SolidWorks is just not very good. Another thing you can add is a edge weld. Yeah. Yeah, so the weld is kind of dumb. No, while you select the tube. There is a way to add a weld. I never spent a lot of time on it, but that might fix the edge elements right here. Or you could fillet them, like you could fillet this edge, but that's a little crazy. That would have to be done in the 4FEA configuration. I don't even know if it would let you. Oh, it does. Okay, just for educational purposes, let's better run this. Hey.
Yeah, what's
Go
up?
ahead. Oh, it didn't do this one. What the hell? Well, whatever. That's where it was failing anyways. Okay, let's try to mesh that again. Do you guys want me to put headphones in? And then let's run it. I'm trying to leave A-arms at 130. I'm sorry, 1230, and we can jump to other parts. So last shot. I've never done this before with the fillet, so maybe that's what SolidWorks needs. ANSYS was fine without it. Oh, that's better. Okay, let's clip that. So we are well below yield stress at this isoclip value. There's a small element here that disappears at 3.5. That's a factor of safety of like 1.3, I think. which isn't bad. And then this whole mess disappears like almost entirely around the yield stress. The only reason that you can almost fully ignore this is that it is welded, which is like way stronger than the metal on its own and is thicker. So this failure here, like though it looks bad in the FEA, it's probably not real. It's probably just like bad FEA. But then this one in the bearing cup is almost definitely real and worth noting because the mesh is so fine, and like this is actually how the part appears in real life, where this is like different. So yeah, what I would do for FEA if you're doing it in SolidWorks is basically take all the steps that I have, try to figure out a better way of constraining the back, try to figure out a better way of like making this a weld, and base your factor of safety on like the failure that does not occur on like tiny edges that SolidWorks can't simulate. So if I were doing FEA on this part, I would say like it has a realistic factor of safety of whatever 4.5 divided by 3.5 is. Yeah. So that is FEA for the A-arms for you. Let's go. Did I save this? I do want to make sure it has. Remember which one I was in?
I have no idea.
As machine. I want to make sure it didn't keep. Okay, good. It didn't. All this stuff. I think it was this one. Okay. Let's go to the knuckle. Are you good so far?
Yes.
Cool. I'm also actually going to go delete some old Zoom recordings because this is going to be a big one. Where is Zoom? Okay.
I think you did I think there's a recording of you doing the MATLAB code.
Yeah.
Right? Okay, cool.
I don't know if this is uploaded. I think it is. All right. What the heck? What's wrong? Oh, that's it. Okay, let's go into the knuckle. Okay, same thing. I'm going to roll it back, see where we start, and see what we do after that. This is like very different than making the arms. This is more like making a traditional part. Okay, so you start with geometry. I went ahead and defined some planes first thing based on the geometry. And then your first extrude should be the like general outline of the bearing cup and of like the shape you want the knuckle to take from a front profile. So like you're kind of thinking in terms of a CNC. Like if you are cutting this out of a piece of stock, this is like the first profile basically plus the steering line. So start here. The reason you want to have this big chunky piece is that the next thing you do is cut the side profile. And this is how it's like been done as far back as I know. Because this is like the next huge bit of material. And after just those two stages, like it already kind of looks like a knuckle. So this is like an efficient way to create the stock you want to start with, more or less, with the center cut out, and then cut the profile. And these values, like these dimensions here, they're based on the sketch with like dimensioned offsets. So you have like a 1/4 inch of clearance for the spherical bearing, and then you have like some more clearance for like the bottom of the bearing and like a spacer. These values are set from the center like wheel bearing. Same thing on the bottom with like the center of the spherical bearing and a spacer right here. And then the widths, you can choose what you want. This one, you have to set the total thickness, but like we've almost always done 1 inch. You have to set like the like angle and where the material goes at the top, and you'll want to edit this when you run FEA to like get it set up well. The thickness here sets the thickness of like the material where the bolt goes. Then you cut. You don't have to do this next, but then I cut or Hannah cut. I don't remember who did like each design step. Hannah did a lot of this, but like I also did a decent amount of this. You cut away where the bearing sits, and these dimensions are like very precise, given by like press fit tolerancing. So this is like exactly what it needs to be as long as we use the same wheel bearings next year. And then you can add the steering arm. So like we added in the steering arm plane, which is defined by this sketch coming from suspension geometry. You make this like really rough looking block. And you just cut away material, like you're just chiseling material away. Oh, well, this is at the bottom, out of order, but that's for the whole, that's like a cut, that's a material cut. This is the one that needs to be like shorter. Like we don't need to have this big of a gap in height. It was based on a different spherical bearing. And then this cut up here, and then the cuts for the holes, bunch of fillets. What are these? I don't know. I think this was Hannah's work down here now, not me. Yeah, boss extrudes for these guys, which is based on this fun looking sketch right here. The reason this has ears on both sides is that the rear knuckle is made as a configuration in this file. And in order to do that, there are like certain quirks in the sketches and like features that you use that accommodate both. So like this sketch has ears on both sides because it allows me to have a boss extrude of these two for the front knuckle, and then a boss extrude somewhere else for the rear, where I just picked the other two sketch like loops. And then if we just take this all the way down, these are like more fillets. The split lines are for FEA here and here, and I'll talk about why. And then made this look nicer and rounded. pretty much done at this point. Yeah, all of these other changes, all these other features are for the rear knuckle. Yeah, so the important things are that you start with the geometry and then create this like big block based on like overall sizes, cut the profile, cut the bearing holes precisely, and then like make the steering arm block and cutouts to fit. And the rest is like, where do you want to have weight saving features? Where do you want to like put your bolt through? It should be in the center. Should be in the center of this face. And it is. I would not suggest you change the knuckle drastically because this is like the best knuckle we have had, I think. But like obviously the steering arm is going to have to change because the location is going to change and you'll probably want these to be closer together. And most likely you'll have to like make it a little bit taller, make it a little bit shorter, move like this hole further in or further out. And that's just based on like the geometry, the such geometry. But I would keep it looking mostly the same. And then the rear one looks very similar, but it has like there. Oh, it's broken. Wait 1 second. There's a cut extrude that got hidden that it needs back. Where are you? This has happened a bunch. I think it's these two. Let's see. Sometimes though, unsuppressing this breaks a bunch of other stuff. Okay, no, looks good. So it has like these on the other side and the steering arm on the other side. Yeah, they're very similar. The only difference really is the steering arm. It is the only difference. Some fun things with the knuckle. Obviously, you need mirrored versions because we have a right and the left side of the car. This is the front left knuckle. When you are trying to flip it, you go into the assembly. And I already have it down here. You choose I'm just gonna look it up. You choose mirror components, and then you choose the component and the like plane you want to mirror it around. What you have to like select that isn't the most obvious thing is for almost every single thing in here, you want to make a left-hand version of the part. So let's say I'm on the knuckle and I want to mirror it around the component origin, doesn't matter. All of these icons right here mean left-hand version, and you choose that down here. So where is it that I am? Where am I? I'm on the freckle. For some reason, it's not being shown. But if I want to make like the true mirror so that like all the features are the same, but they're just like flipped, I choose left hand. These just like mirror X or Y and not both, or they like flip it upside down or they flip it. It's stupid. I don't know why they exist at all. But yeah, that's about it. That's the only trick. And then it's also easy to flip the drawing, which I'll show you later. But SolidWorks has a tool for that as well. So let's go back into the knuckle and I'll go into the FEA for this really quick. Let's use bump 3G full. No, not full. So we're going to use like, this is so wrong though. Okay. Worst case loading for the knuckle. Well, we'll start with the fixtures. We have a fixture here on this split face, which is why we created it. That says it can't go up anymore. And that's because we're modeling that arm as fixed. That's like the worst case for the knuckle. And then here, these are fixed from rotating or from like moving. And these are elastically supported, which is like, honestly, you don't need it, but SolidWorks like said it wasn't constrained enough without this. So I just added an elastic support, which is something stupid. And then we have a roller slider here as well. So that's like accomplishing the upper arm fixture. This remote load is similar from the bottom of the wheel. In my FEA, I put it onto the bearings themselves, which is saying that like in the worst case loading for the knuckle, the arm is like totally static, is taking none of the load. The knuckle has to do all the work itself. And this is a much higher load. I was actually able to use 1680. So let's instead do 2 Gs for the full car. But this is an upward load right there. In the mesh, I'm pretty sure I just did a curvature-based fine mesh and it was enough. This is easier FEA. This is more like traditional FEA. Oh, that's very fine. Shoot. All right. All right, so we can see that this thing is like very strong. And we also see a lot of green, which is good. You want to see as much green as possible in your part because that means the weight, or not the weight, the stress is like well distributed. And not only that, but like this has a factor of safety of almost 5 for this load, which is a massive load. So that's why this part is like so good. Granted, it might be the case that we should consider load being applied, quote unquote, up here. Because that's where the actual like resistive force is felt. And it's not so much here. So we could instead model this as like some kind of elastic fixture and this as a load applied. But SolidWorks doesn't like that very much. I encourage you to think of a better way to like apply loads to this part because yes, it is strong and it doesn't fail and we know that, but it shouldn't really be this strong. Like it shouldn't be able to take 5 Gs of bottom impact because it is just aluminum. Like I think there's something that's a little conservative in this FEA, but what the hell, it looks really good. And it's like the best I could think of. So that's knuckle FEA quickly. I didn't want to spend as much time on it. It's easier. And that's why I think the part shouldn't change that much. This is the same FEA that we did for past knuckles that required the 5-axis CNC, and they were way weaker. Like they almost failed or like had higher stresses at least. So there is something to be said for this part, just like being a lot better. Cool. Knuckle. You think we can move on to Hubs or Goofy?
I have a question regarding
Yeah.
your designing process. I know
Yeah.
like we're not going to change that much for the next year.
For the knuckle,
when you're for the knuckle, but when you're designing this knuckle, when you're like cutting out materials like from the very first step,
Yeah.
like how would you determine like how much to cut or like what's the geometry of the cut? You just like wing it or
you have to wing it the first time and then you run FEA
Okay.
and you say like, is this good?
Okay, and then you change the geometry like according to the FEA, right?
Yeah. So like
Okay.
I was the one that designed like up through here, maybe up through here. I don't know. I did the first few steps. So like I created a very rough knuckle with different dimensions right here, right here, and right here. I don't remember what they were, but it was like either thinner or thicker. And if it was thicker, the FEA showed it was too strong. And if it was thinner, the FEA showed it was too weak. And that was like what I really had to play with in this initial block was like the thickness at the bottom and the top. So those were the first values that I started changing. Then once I had those like pretty narrowed in, I started playing with these values. I always kept this thickness at 1 inch, but like I messed around a lot with these up here until they were like good and the stresses were good. And by stresses are good, I mean, you see a lot of green. The stress is pretty like constant. There's no like corner that's too tight or edge that's too small or hole that's too close to an edge. So like this fillet got really tight at one point and I had to like change some stuff. This fillet got really tight and I had to change some stuff. This hole got too close to the edge and I had to change some stuff. Question, why do you think there's no fillet right here?
I guess it's not a place where the stress concentrates.
Yeah, there's no stress.
Yeah.
Because all the stress goes back to like the center of the part or the other mounting position.
Okay.
You can also just file this down after you make the part. So that's the other reason. But yeah, that's how I started out. Unfortunately, you kind of have to finish the knuckle, at least kind of, before you can really get good FEA feedback, but it doesn't take super long to finish a designed knuckle, especially if you're like referring to this one. And a lot of the stuff is like,
yeah,
similar. Okay, let's go to the goofy arm.
Sure.
I think the hub, like I didn't change the hub at all. I think the hub is just going to remain. Okay, goofy arm.
What's the proper name for goofy arm? Is it like just like upper control arm or
Upper
something?
control arm or J arm.
Okay, gotcha.
Yeah. The goofy arm is in its initial state not called goofy arm optimized. It's called goofy arm V1. Okay. It's ugly. Oh, what the hell? No, it's not. Oh, that's why. Okay. It's because I'm in the spline version. Well, goofy arm V1 was based on just the chassis sketch. And then I brought in the suspension geometry sketch. And then I defined a plane back here. And then I built up the goofy arm from sketch 2, which is this one. So from just the geometry, I did like a very rough sketch around it, rectangles, extruded the goofy, and then went to work on like cutting the things I knew I needed. So like a hole for the shock to mount with a bolt hole, a hole for the inside to mount with a fillet, and then like a stupid looking wafer. And then I was like, I hate the stupid looking wafer. Let's make it thicker. This might break. Okay, let's make it thicker. So then I did a thicker wafer. and I did like a combine so that it was all one part, yada yada. Well, before I get to that point. So you can get to this point pretty quickly with like just chunky rectangles and like the same bearing cup, which is from the same, where is it? There, from the same sketch block. And then big change right here. Reason is from this, I ran a optimization study. And the optimization study, if I can just show the results, I don't know if it'll let me. The optimization study, which like you've seen Carlos or Sean run maybe. Damn, it's not saved. It shows you like where you can keep and remove material. So what I did was like took that feedback, generated an overlay. You can overlay study results with one of these. I don't remember where it is because it's been so long, but it's somewhere up here. Or maybe it's like from within the study. I don't know. I had this part and like overlaid the study on top of it. And then I cut away everything that was like going to change, which was most of the part. And then brought it all back. And I brought it all back by like sketching the outline of the resulting optimization FEA, which you know is like the blue and yellow like elements that are kind of like pieced together by SolidWorks. And I just sketched this spline, which is very freehand. Splines are like very freehand. They're not very well defined, but they do give you like very nice natural looking shapes, which are better for stress concentrations sometimes. And in this case, they are. Upside down. There. So then I brought everything back to like meet the pieces that I had kept and then combined them so that it was one part again. And that's how we got to like this design. The topology optimization, Carlos and Sean have already run stuff like it, but basically what you do is you set up like all of your fixtures and loads from your worst case. And then, well, when you're creating it, you don't do a static study, you do a topology study, or you can also do a design study, but topology is better. You do a topology, and then it gives you like these other options here, the goals and manufacturing controls. And for goals, you want to give it usually a factor of safety constraint where it goes no lower than 2. And for manufacturing, this says like, where can you remove material? So like, can you remove material coming from one side down? Are you only going to remove material if it's like a through hole? And then SolidWorks will like iterate and run the study a bunch of times and say like, oh, it's best if you remove material here. It produces like at least this factor of safety and it's light. So that's how you generate the topology, but then you overlay and like resketch basically. Some things to note with this goofy arm, because there's a bearing cup, you like need a certain height right here. Like this has to be a certain height, but because there are big holes here and a lot of stress, this like has to be thicker, has to be at least an inch. So this one has a severe taper to it, and this is the one we made. It has a taper to it. That's the reason it requires like at least a flip on a 3-axis or ideally a 5-axis CNC, that and the complexity of the bearing cup. But if you don't have a bearing cup, you should just keep this all the same thickness because you need a bolt hole here. And then it's like a much easier thing to create, like to machine. And that's why the one we machined ourselves is all the same thickness. Other things, this shock geometry is the same as in the front, where like the length here is the shock lever arm, shock moment arm. You have to make sure the shock doesn't interfere with like these walls, so they have to be at least 1.18 inches apart. That's the dimension, and that's written down somewhere, and you can also just ask me, but 1.18 inches. You also have to make sure the shock doesn't like run into this wall or this wall when it pivots. You can move where the shock is mounted, front or back, and it just causes like this mounting hole to change, which would just push this entire sketch back. Like this box would be pushed back or forward based on like where the shock is mounted. So you have like a bunch of freedom there. But you should try to keep it generally like along this path because it's better for loading. This path, which connects like the center of the mount to the center of the spherical bearing. So you can see they're pretty close. You don't want to have fillets that are too tight in like these inner corners because they will fail. So this is actually too tight. And that's why like the updated arm is wider. But if we look at, I don't even know where the one is that we cut ourselves. It has like more cutouts here because it features no spherical bearing, which is like what caused such high stress in this part. So the one we cut ourselves has no spherical bearing, which means it can be like thicker on the end so that it's the same thickness. And that also means we need more weight saving cutouts. But it was like 30% lighter than this one, which is what we made for 21. Or like what we run on 21. Where is that file? I don't know if it's in the GrabCAD. Yeah, I don't think it's in here. That's about all that I have for the goofy arm. You basically just like use the suspension geometry as your guide to start out, and then topology optimization gives you the shape. FEA on this is a little bit tricky because again, you have the bearing cup, and SolidWorks doesn't like that. But let's see what I do. Here we have a rotational constraint that allows this to pivot. Here we have a roller slider because that's where the tab is like holding the goofy arm from side to side. Here we have another rotational constraint. Or sorry, not a rotational. Here we have like a movement constraint that fixes this in place because this should not be able to like move. But Sean actually did a better job of this, where instead of doing like zero radial movement at all, he used reference geometry and said, this just can't move in the direction of the shock. So it can't move like, well, we'll do this and like cheat and make it simpler. It can't move up. That's sideways. Where's that? There, flip it there. What the heck? Can't move up, not down. Why is that being so dumb? What the hell? The arrows aren't flipping. Well, whatever. He made it on reference geometry so that it couldn't move in the direction of the shock, which is better. That's more accurate. Then you apply an external load, very similar to what we did for the A-arm. This is a front load though, so it's from the front of the tire, not the bottom. And then you need a very fine mesh control on the bearing cup again. And then we'll rerun it. It's probably going to show us that it fails at the bearing cup. And I'll tell you why that's fine. Although this is with a much lower front load, so it might not. Come on. Might not finish at all. Well, the reason it does not matter whether SolidWorks tells you there's like 1 or 2 failing elements in the bearing cup is again because like there's just a lot of tiny edges in there, but also because it tells us that the bearing cups should have been failing in the wafers every year for like the entire history of Baja based on the designs we've been using and the loads that we use in FEA, but they never have. So either SolidWorks does a bad job of FEA in the wafers, I think that's what it is, or the loads we've been using are like 3-4 times higher than they should be, and that's the issue. Okay, it actually worked here. SolidWorks is doing a good job today. Good job. It's because this load is so low that it hasn't failed. Oh, it's because I'm using HAdaptive. Nice, I didn't realize that. This is a different solver that is like better within SolidWorks. I'll show you how to turn it on. It takes longer, like it's solving 3 loops instead of just once. But HAdaptive, it means like it's going to solve it. It's going to back check to see whether like the deformation of the elements is matching the assumption that it made initially. Because there's like a lot of assumptions you make in FEA before you can solve for stress. And then if it doesn't match, it like fixes its assumption and tries again. That's cool. I didn't know I was using. I must have done that a while ago. But yeah, I don't think our loads are off by like an astronomical amount. So I think SolidWorks is just bad at doing FEA in wafers. But maybe this solver is better, and that's why I used it. I did these FEA like a year and a half ago, so it's a little foggy. you want to try to wrap up by 1:30? I think we can.
Yeah, sure. That would be good.
Right. I think I'm just gonna like touch on the hub super briefly, and then I'll go into drawings again briefly, but I can't stay on for much longer. Just gonna do one more of those. So one thing you'll notice as it goes through these steps is that the peak stress is slowly increasing because it's like refining its calculation. So it went from like 3.2 to 3.56. It can also decrease if it finds out that like an approximation was too aggressive or like whatever the word is. Hopefully it's almost there. Come on, SolidWorks. Aha. Okay, it's done. So it went all the way up to 4.35 there. This shows honestly pretty accurate, believable results. That's cool. Looks like the highest stress, most of the part sees very little, but then there's a lot of stress that is like right on the outer bolt hole where the shock mounts and on the bearing cup. And this is probably still way too high because like there's no way all these tiny little edge elements are really seeing twice as much stress as everything else. But I think this is like pretty good. The way that I got the H-adaptive solver, if you right click up here and go into, I think it's properties. Yeah, so here's the solver. You can select it manually and there's like a bunch of choices. You usually don't want to use any of these. These are bad. Large displacement means that it's going to like recalculate for like any displacement that is higher than the solver initially anticipated. So that's a good thing to have if you can manage it, like if you have enough computing power. And then adaptive method, this is H adaptive, which is what I was running. It took multiple steps, but usually it doesn't run any. So this is like minimum number of loops is 3, and it has to hit 98% to stop before then. You can also run P adaptive, but I don't even know what that is. We learned about H in my FEA class, but like that class sucked. Don't take it. And then we don't have any thermal stuff. Yeah. So maybe run H adaptive for the goofy arm. Maybe run it for the arms also because they have bearing cups. It seems like it helped. It just took a lot longer. Okay. Let's really quickly look at the knuckle. Sorry, at the hub. I don't want to change the V1 file. There's no use. But I will change this one. Okay. What laptop do you have, Chandler?
So for like all other school stuff, I have a MacBook Pro, but for CAT, I have a really basic HP.
Okay.
Yeah.
Do you have any like strong computer at home?
Probably not. I'll probably trade in my my HP for a stronger one.
Okay.
Yeah. Is it necessary though?
It just takes a long time without it.
Because like I feel like my laptop it kind of sucks like in every other aspect, but it's fast enough to run SolidWorks. Like in my experience of like CADing on my computer, I feel like it's fast enough.
Yeah. You're probably fine. Maybe C2 has something strong. You're going to want like something that's strong enough to run a topology optimization in less than like 15 hours.
Okay.
Because that's how long it can take if you have a slow computer. Whereas mine
wow.
took like 4 hours, 5 hours. It's got like 32 gigs of RAM and a decent processor.
Oh wow. Okay. I'll think about it.
Okay, the hub has been this way for 5 years now. The lore is that it was designed by Kevin, but I think it even predates Kevin, basically, like in essentially this form. I think it was actually designed by like Ellen, who you've probably never heard of, or maybe even Gambo, who comes to alumni design reviews. So you will figure out who that is. But it looks like this as a revolve feature. I tried to mess with this and like tune it so that it had better stresses, and I achieved like a fraction of success, but it wasn't worth changing the file, so I just kept it as is. You're welcome to try also. It starts with this revolve, which does most of the work. Well, I guess not just that revolve. And then this cut does like the rest of the bulk. It's just like a top view of ellipses. The whole thing is like ellipses and circles. There's like no straight lines, which is crazy. Then a bunch of material cutaways. These are where the rotor bolts in. Material cutaway at the bottom. A bunch of fillets. Look at all these fillets. Tap tool for the rotors. More fillets. The only big thing down here that I changed and that like is written down is the spline, because they had it almost right, but not perfectly right. It should be 20 teeth, a 24/48 diametral pitch. That's not a typo. That's not the same as 24. 45-degree pressure angle in class 4. So 20 teeth.
What does class 4 mean?
Class 4 is the tightness of the fit.
Okay.
And Bob Ezor is the one that figured that out for us. So if you want to change the hub, some things to note are this face to this face. That is the contact point that like goes all the way up to the CV, the base of the CV. And this is what sits against the knuckle. So you'd have to keep this to, I think it's an inch. Yeah, you have to keep that to an inch. The spline has to be the same. The distance between like these rotor mounting points has to match the rotor. And this diameter from like here to here has to match our rims, which are and have always been 144 millimeters. But that doesn't mean that you can, like, that you can't change the rims if you want to. It's just what they've been in the past and what we have on hand. The rest, I believe you can do whatever you want. But if you're working on other parts, don't bother. Like, only if you have time and like really want to grind away for like a fraction of a pound of weight savings, is it worth changing the hub? Like, there are so many other places that you can save weight without like spending hours and hours and potentially getting nowhere. The time input is huge to change this part because it's like hard to find something to change unless you like really have to get a new clearance or like you really have to put a new rotor in or something like that. It's also a pain to work with because it's like there's so much information contained in like just 2 or 3 steps at the beginning of this file. And if you want to change one of these, it like has a waterfall of broken fillets and other sketches and things like that. So it's not worth it unless you really have to change something, I think. Like, you're much better off coming up with like really good load validation and FEA for the arms, load validation and FEA for the knuckles, a good goofy arm or a tube to replace it. Spend your time on coilovers, spend your time on carbon fiber tie rods, spend your time on better half shafts that are lighter or like that sort of thing. Don't spend your time on a hub. And you already have 4 of them. So like, yeah, that's what I have to say about this. But it can always be improved. Like, the one thing that I think is too weak still is this like little portion of material. I think it's like very thin and it scares me. And that's what has broken in the past. That's where the stud is pressed in. And the one thing you might have to change if like for some reason you can't figure out how to fix it on the caliper end is that it was interfering with the caliper here and here. But you really don't want to we cannot take material off of this outer edge. So that should be fixed on the caliper side. Other than that,
is it possible to make like the edge, the one you just talked about, like, yeah, like thicker?
Yeah, you could make it thicker,
Yeah.
like going up. So
Yeah.
You could design that and like have them made, but we already have 4 that are like
Sure.
this.
Okay.
So.
Yeah.
But yeah, you're right. Like, there is a little extra length even in the studs that extends past, right? Like the thread of the stud goes past.
Mm-hmm.
So you could thicken this.
I see. Yeah.
It's a good idea. Maybe just make that design change and don't make the part, something like that.
Yeah. We'll see if like how our budget goes.
Yeah.
Yeah.
Okay. Let's open a drawing. Where is it? There. Okay. Okay. Drawings, I would like to take a long time to talk about them, but the best quick advice I can provide is look at old drawings for that part, especially mine. No shade to Gwen, but her drawings weren't as good. Kevin has very good drawings, but those are like in a super old GrabCAD and the parts are outdated. So some of the parts, the knuckle at least is outdated. So I don't know if they're as useful. Also, look at Benny's drawings. They are nice. Like he has probably the best drawings on the team right now. From this year and from next year. And my other advice is let SolidWorks do work for you, because it actually does a pretty good job of doing work for you in the drawings. What I mean by that is shown here as an example, is if I want to flip to the right knuckle, this is the left knuckle. When I was making the front knuckle left hand, all that I did was like click on the base drawing. So you just have to figure out which one that is. Let's see. Probably this one. Yeah. And you mirror it. That's it. I think where is it? There was one drawing where I like didn't realize you could do that, and I might not have done the mirror, and it might be the knuckle, or it could just be that I used a different configuration. Oh, I did. Oh no, it's here. It's here. That's why. It's the front knuckle right-handed. So I mirrored it horizontally, and that does literally everything. Like if let's say I want to make a new drawing page. Before this one. So I'm just like copying the exact drawing. This is identical. And now I want to go in and mirror this horizontally. Done. That's it. You just have to like move stuff so that it fits on the page nicely. And that's the only change to make. The reason it did all of them at once like that is that another thing that I let SolidWorks do for me is derived views. So if I start with the base view, which you do, I don't know like what your drawing experience is, but you import a model view by going to drawing, model view, you pick the part, you pick the view that you want and you insert it, and then you like dimension everything. From that view, if you want to like create a derived one, you do projected. So I'm like from this view, I just hit projected view, and now I can insert the top, which is what I have there. I can insert the bottom, which is what I have like over here. I can insert the right, which is what I have there. I can insert the isometric, which is what I have there. So you can see where all this stuff came from. It's just like projected views everywhere. And then they're all like tied together. Another thing you can try to do, but it's not as good, is if you click on annotation, model items, you can have it import model items from the drawing, and it'll try to give you all the dimensions that you need. It's not great. It's worth a shot for simple parts, but really not for the knuckle. As for like how to dimension, there are way too many rules to just cover right now, but typically you want to think like, if I were machining this, where am I going to datum? Like, where am I actually going to zero the machine? So for the knuckle, that could be the very bottom. And then dimension everything based off of that. So this hole is based off the bottom. This center of this hole is based off the bottom. This hole is based off the bottom. The total height is based off the bottom. Some stuff is like not included. So like we provide them the step file, and if it's not included, they will just look at the step file. But all the big stuff, like you should find a datum for it. All of the like bolt holes, you shouldn't dimension yourself. You should do a whole call out, and SolidWorks will do it for you. That's another thing SolidWorks does for you. So this is a whole call out. 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 And then the last thing is like, not last thing, actually, two more things. Adding these little tolerance bubbles. You only need these when it's like a very precise hole. So this has a bushing press fit into it. This has a bearing press fit into it. This has a bushing press fit. Any press fit needs like a very precise hole. So the way you do that is you like create, I'll just recreate this one. It's a +1 to -0. You create the dimension like this. If I want it to be 3 decimals, it's here under tolerance and precision, 2.327. And then if I want to have tolerance, it's under tolerance and precision. And I choose that. The plus is 1, and the minus is 0. And you're done. You can also add little notes to your dimensions. So like this says through to next. You can say like for bearing. And if you ever want to add that stuff, it's down here in the dimension text. So if I wanted to say like, go out, like for bearing, stop it. For bearing press or whatever. So you can add little notes like that. You can also add notes to the drawing by going up to annotation, note. All interior fillets are this unless otherwise specified. You can also say like, refer to CAD file for all dimensions not shown, whatever. And then another thing that I'll mention on this drawing right here, this is a section view. So when you're inserting, drawing a view, this is to insert like a normal model view. This is to insert a projected view based on another view. You probably won't need auxiliary, but it's like a projected view at an angle. Section view is super useful. It lets you like cut the part. So this is like a cut that I made. And this is B, and this is section B. And it'll like go at an angle, or it'll go vertical, or you can do horizontal. It'll like show the projected view up or down, side or side, like from the line you've chosen to like through the rest of the part. So that's how I was able to get this. Other ones up here, you're not going to need that. Detail view is if you want to like look at something very precise and like create a view based on it. You move that around. Never used this. I don't know what it is. Don't use standard preview. Break view, if it's a very long part, can be useful for like a tie rod. And it just like creates a visual break. Like that. So then if you have like a super long tube, instead of looking at the whole last tube on your screen, you can just look at the ends and say like, there's a break in the middle, and then the length is like still accurate. All the dimensions are still accurate. You just don't have to look at as much. Other annotations, you should put a center mark, on all of your holes, which is here. You should put a center line on holes if they're like not visible. So honestly, I missed a couple. Here, I should have one, and here I should have one. Well. And then for the VR3 documentation, you'll have an assembly drawing, which requires a whole other set of like rules where you need like a table with a bill of materials or a cut list. And then you'll need like all these balloons to point to different tubes in the assembly. But you can just look at that when it is time and ask Nico or Takeo or me. Preferably, don't ask me first, please. But like, there's gonna be people who know how to do that, so you'll have like resources, and you can just look at my old files as well. Last thing is format, which is this down here. If you right click and edit sheet format, that's how you can edit all these boxes. So this should have said 75 aluminum. Finish is as machined. You could say drawn by like initials, comments, typically don't have any. The title should autofill, but if it doesn't, you can edit that. The system should be suspension. And if you want to have like the Bruin Racing format, there's a folder for it with instructions in, oh, this is my personal drive, in the Google Drive, which I already added. And it tells you like how to download the files and use the format. That's about it for right now. There's a lot more for drawings that I could talk about, but another time, or just ask like other people who will know, or look at old files. Do you have questions on drawings, like the stuff that I talked about?
Not at the moment.
Okay. When you're actually dimensioning things, you'll have a ton, because like GD&T, geometric datum and tolerancing, that's like the rules that you're supposed to follow when you add dimensions. And they're just nuts. Like, I could not cover all of the instances that you'll like see and all the dimension rules you'll need to know. It would be impossible.
Yeah, I'll definitely watch videos on GD&T.
Yeah. Yeah. You can also just talk to like the manufacturers who are making the parts to see, like get feedback from them on drawings.
Okay.
It's a great resource. All right. Well, I'm sure you will have questions that come up. You can definitely ask me questions like about what we talked about today, or anything else by the end of the year. And then if you have like burning questions in July that like no one else can answer, you can ask. And I guess if no one else can answer stuff in the future, you can reach out to me, but like I'm not going to be super responsive once I'm working, probably.
For sure. I'll
Just
try
like,
not to.
yeah, just try to like use other team resources, old files, Google, that sort of thing first.
For sure.
But like obviously there's some things that only I can answer because it's stuff that I did. So then ask me again. Yeah,
All right.
I think that's a wrap
Thank
for
you.
today.
Thank you very much for your time.
Yeah.
Yeah.
Of course, I'll save this and upload, and I hope it helps.
It definitely helped a lot. Yeah.
Good. All right. Thanks, Chenwei, and good luck with all this stuff. I do want to like be there to help if you get stuck on something. But you're also going to learn more if you like grind on it yourself for a while. So
For sure.
you
Yeah.
can strike a good balance there.
Yeah. All right. Thank you, Ben. I'll give you updates. Yeah.
Sounds good. I will talk to you soon.
All right. Thank you.
Yeah,
Bye, Ben.
Bye.